Hey you guys, so this is problem number 46 from chapter 4 from the section on mesh currents. So before we talk about what we're looking for, let's describe the current. We have three power sources. We have an independent voltage source with 50 volts value. We have a current controlled dependent voltage source of value 9I delta, and its value is controlled by the current across the 5 ohm resistor. We also have a voltage controlled dependent current source, and it takes its value from the voltage drop across the 2 ohm resistor. So we got two dependent power sources, and the rest of the values are we've got a 4 ohm resistor here and a 20 ohm resistor here. In part A, what we're looking for is we're trying to determine which of these three power sources are actually generating power. Not all of them do. One of them is actually receiving a charge and dissipating power. In part B, we're looking for what is the total power dissipated by this circuit. So of the three power sources, I'll give you guys a hint. Two of them generate power, and one of them is dissipating power. So you take the two that generate power and you add them together, and that will tell you how much power this circuit is generating, or delivered by this circuit. Okay, go ahead and pause the video and try it out, and then unpause it when you're done to check your answer. Okay, so the concepts you need to understand is the fact that the mesh current uses Kirchhoff's voltage law, which says the sum of the voltage drops around a closed mesh must equal 0. You also need to know what a mesh is. A mesh is a connection of circuit elements that begins where it ends. So it makes a closed loop, and it contains no other circuit elements inside of it. So this would be a mesh. It begins here, goes here, 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 and here. That would be an essential mesh. And that Kirchhoff's voltage law applies to that mesh. This is also a mesh. 1, 2, 3, 4, 5. It begins where it ends, but it does not, the mesh current will not work on that, because inside this mesh you have other circuit elements. So the mesh current method works only on the essential meshes, which contain no other circuit elements inside of it. So knowing that, it's pretty intuitive to identify three meshes. We can identify easily one here, and one here. So those are going to be what we use for Kirchhoff's voltage law. So let's go ahead and get started. So we're going to identify the mesh currents inside our three essential meshes. In this circuit, I don't know what that current is, so I'm going to call it IA to match with my paper so I can cross-check myself later. This one I don't need to name because the schematic already gave me the name of this mesh current. They called it I delta. And this one, they gave me a name for this mesh current too. They told me that it's this current 1.7 V delta. Now, you can call it that if you want, the positive in this direction, which is what the author has told me. However, for me, and this is strictly a me thing, because I tend to make mistakes if I don't keep everything in a consistent manner. So I'm going to call this, because I take everything in the clockwise position. For me personally, it reduced my error rate. So I hope I'm not creating confusion for you by doing this, but I prefer to turn it clockwise and call it negative 1.7 V delta. You can do whatever makes you feel comfortable, but that is what leads for me personally to fewer mistakes. So I'm going to call that current negative 1.7 V delta. So now we can begin writing our mesh currents. So mesh at IA. We've got a current IA entering the negative terminal of the 50 volt independent voltage source. That tells me the first term of my equation is negative 50. After that, we have a voltage drop, which we can call V delta, but it won't help you very much if you call it V delta. Actually, it doesn't make any difference, but the way I have it on paper here, you can say plus V delta, it would work, but I'm going to call it plus 2IA. So our equation simply has to be sums of voltages. So a voltage is current times resistance. So we're going to call this 2IA. The next voltage drop we encounter is across the 4 ohm resistor. So that's going to be 4. That's my resistance. My current is the net current of IA minus I delta. That's my next voltage drop. My final voltage drop in this loop is this voltage drop. The voltage drop across the current controlled dependent voltage source, and it is already a voltage with value of 9I delta. The first terminal that the current encounters is a plus, so that tells me this term is going to be plus 9I delta. It's probably might be a little confusing because this term is a current, right? It has a current term in it, but yet it is a voltage drop. And the reason is that this symbol is the symbol of a voltage. So it's a voltage, so if you were to take a voltmeter and you would plug it to the two ends of that terminal, it would pop up a value that is 9 times the value across the 5 ohm resistor. So if you had a varistor here, so if you had something that a current controller there, and you brought the current down, it would change the value of that voltage. So this is actually a voltage term that contains a current, which may be very confusing. So, but that's what that is. In the second mesh, we're going to start right here. So I delta is positive current that enters a negative terminal. So that tells me the first term in my equation is negative 9I delta. The next term, our next voltage drop, is across the 4 ohm resistor. So V is equal to IR. My R is 4. My I is a net current of I delta minus IA. That's my next voltage drop. The next voltage drop across the mesh is across the 5 ohm resistor, and that's just going to be, the only current through that is I delta, so that's just going to be 5I delta. And the next voltage drop across that is across the 20 ohm resistor. So our resistance is 20, our net current is I delta minus a negative. So minus negative 1.7 V delta. A negative and a negative is positive, so that tells me this is really I delta plus 1.7 V delta. That's that net current. And here, it may seem a little confusing that this is a current term which contains a voltage. So, but it is in fact a current. So this current in this mesh is controlled by that 2 ohm resistor. So if you had a varistor and you could tweak it up, that resistance up or down, it would control how much current is going through in that mesh. So that is, I got current, resistance times current, and that is all I have for that mesh. Now, let's think about all our unknowns right now. Right now we have, let's see, I got 20. Oh, yeah. Okay, so that's my second equation. Okay, so my third equation is going to be from this mesh here. So that's going to be, first there's the 20 ohm resistor. Okay, so I'm going to write my third equation here. So the first voltage drop is across the 20 ohm resistor, and that's going to be times a net current of negative 1.7 V delta minus I delta. And now we're going to add this voltage drop. So this voltage controlled dependent current source has some voltage drop across associated with it. And we don't know what it is. So we're going to call it Vx. However, I want you to notice that when positive current goes through a voltage, positive voltage, it goes through a voltage rise. That means, so it goes from negative to positive, right? So it's going up in potential. It's generating power, it's going up. So that means if we have negative current, then the potential must be going down. So it must be a voltage drop, which means it must go from positive to negative. Negative current will go through a positive a voltage drop. So that tells me I'm going to call this some unknown voltage drop, but it goes from positive to minus, and we're just going to call it Vx. So this is going to be plus Vx is equal to 0. Okay? So now my unknowns are I delta, IA, V delta, and Vx. We have 4 equations but 3 unknowns from our 3 meshes. That means we have a constraint equation that's going to provide our 4th equation. So we have 2 equations that can provide constraint equations. So I delta, we can say I delta is, we can either use I delta is equal to IA, the sum of this and this. So, let me see. We have this current through there and that current through there. Actually, let's see. This current and this current. That won't help me. It's a little easier to construct the constraint equation from V delta. V is equal to IR. So that's actually what I ended up doing here. So we'll just go with that. So V is equal to IR. So V delta is equal to 2 times IA. So our 4th equation is going to be V delta is equal to 2IA. We want everything on one side for the sake of constructing a matrix. So we're going to put the V delta there. And we're going to go 2IA minus V delta, that's equal to 0. That's going to be our 4th equation. Let's put it here, 2IA minus V delta is equal to 0. Okay, so now we have 4 equations and 4 unknowns, and we can solve this problem. Okay. And I just want to match my matrix here. So we have IA, I delta, V delta, and Vx. So let's go through each term one by one. So this one, we have 2 IA, and then we have a -1 for Ix, and then a 0. That means this is 0, and that's 0. That's the first line of my matrix. That's my first equation. My second equation is this one. So 20 times 1.7 V delta, -1.7 V delta is 20 times -1.7. So I got -34 for V delta. And then for I delta, I have -20. And for Vx, I have 1 coefficient and 0 here and a 0 here. Alright, so 0, -20, 34, 1, 0. Okay, that's good. Now, let's go from left to right and account for every term here. So I got -50, which will actually go on this side of the equation as +50. That's the first term. Then I have a 2I delta, IA, so that gives me 2 here. And then I got a 4IA, so +4. And then distribute it through, I got a -4I delta, -4. And then I got a 9I delta, so +9. And this is 0. I have no V deltas and no Vx's. That's the third equation. And now the final equation, let's start over here. We've got a -9 for I delta, -9. Then we got a +4. And then we got a -4 IA. Then we have a 5 I delta, so +5. And then we got a +20, +20. And then we have 20 times 1.7, that's 34. So V delta has 34. And 9 and negative 9, 4, so 4 and 5 is 9, so positive 9 cancels out with negative 9. That puts 20 here, so this is just 20. And then that is it, and we got zeros everywhere else. So 0 here, 0 here, and let's just substitute this with 5. Negative 4 and 9 is 5. So 2 and 4 is 6. Okay, so let's put that matrix in and solve everything, find out what everything is. Okay, so we want a new matrix, 4 equations and 4 unknowns. 2, 0, negative 1, 0, 0, 0, negative 20, negative 34, 1, 0, 6, 5, 0, 0, 50, negative 4, 20, 34, 0, and 0. Okay, gonna take a second to check to see that's what I got the first time around. Okay, so it checks out. So what the answers I should have got are, you should have got IA is equal to negative 5 amps. I delta is 16 amps. V delta is negative 10 volts. And Vx is negative 20 volts. Okay, so in part A, we want to figure out which circuit elements, which power sources deliver power and which power sources dissipate power. So we have 3, right? In the first mesh, we have the 50 volt independent voltage source. So let's figure that one. Does it deliver power, or does it absorb power, or does it deliver power? So P is equal to VI, of course. The V is simply the 50. Now recall, the sign is very important. The current enters the terminal, which means this is negative voltage, negative 50. The I is the IA, and we found that to be negative 5. That gives me positive 250 watts. So that circuit element is dissipating power. It's receiving a charge. Okay? It's absorbing power. Now, the next power source we have is the power of the 9I delta. Okay, so the sign that the current enters, and of course P is equal to VI. The value of that voltage is 9I delta. It takes this value from the current across the 5 ohm resistor. The terminal that the current enters is a negative. That tells me this is negative. Okay? And the I, the current through that, is a net current. And the net current is IA minus I delta. Okay, so then it's going to be negative 9 times 16 times IA is negative 5, and I delta is negative 16. Positive current. Oh, I'm sorry, you guys. I have a mistake. So I have a mistake because the terminal that the positive current goes through, the positive current is the IA current, and the first terminal it encounters is a positive. So it goes from positive to negative, so that tells me the voltage is actually a positive. Okay, so when you do that, 9 times 16 times negative 5 minus 16, you should come up with negative 3,000 424 watts. So negative power means this particular power source is delivering power to the circuit. So now the last power source that we have to account for is the 1.7, the voltage controlled dependent current source. So this current, so we know P is equal to VI. We know what I is. I is the negative 1.7 V delta. The P, so that's the I, right? Even though it has a V, it's the I. So the V though is the Vx. Okay, that's the voltage drop across that power source. So that's going to be negative 1.7. So we got negative 1.7, the V delta is times negative 10. Okay, so that's the V, and then the I, or that's the I, excuse me, that's the value of the current. And the first terminal that it enters is a positive terminal. So the Vx, we're going to take positive Vx, and positive Vx is negative 20. That was the value of that. So now when you multiply everything together, you should come up with so the power of dissipated by the 1.7 V delta current voltage controlled dependent current source is negative 340. So that tells me that that power source is delivering power to the circuit. So in part A, the answer would be the 9I delta current controlled dependent voltage source delivers power to the circuit, and so does the 1.7 V delta voltage controlled current dependent current source. Those two circuit elements deliver power. The 50 volt independent voltage source is actually receiving a charge. It's dissipating power. So that is the answer part A. Now part B asks the question, how much power is dissipated? There's only two circuit elements that generate power, right? And so now we need to account for how much power is dissipated, right? So that means that we're going to keep that there because we need that. That's one circuit element that dissipates power. Now before we do that, we're clever engineers, so we're going to add together the total power delivered as a check figure because power delivered had better equal power generated, right? So let's add the two circuit elements the two dependent sources that generate power, and see to come up with a check figure. So we got 3,024, right? So if you're in an exam, you should do this. So you know which circuit elements deliver power, so that's going to be the two dependent sources. 3024 plus 340. They generate a total of 3,364 watts. So whatever you come up with as far as how much power is dissipated by the resistors and the independent voltage source had better equal 3364. So if you have something easy to if you have a problem similar to this, make sure to calculate what the power delivered to the circuit is, so that you can have it as a check figure. So now we have, what circuit elements do we have to account for? We need to account for the 2 ohm resistor, 2, 4, 5, and 20. So we have 4 circuit elements to account for. So power is, of course, I squared R. Since we're using them, there's 2 options for power across resistor. It's V squared over R or I squared R. The mesh method naturally lends itself to the I squared R. So that's what we're going to use. So our R then is 2 across the 2 ohm resistor. Our I then is IA. And IA is So negative 5 squared. So now, that's that one. So the power across the 4 ohm resistor, our R is 4 and our I is going to be IA, which is negative 5 minus I delta, which is 16 squared. Now the power across the 5 ohm resistor is I squared R. The R is 5, the I is I delta, and that is 16 squared. And then the last one is the power across the 20 ohm resistor, I squared R. So the R is 20, the I is going to be I delta, and I delta, it's going to be I delta minus negative 1.7 V delta, so it's going to be I squared I delta plus 1.7 V delta. So I delta is 16 plus 1.7, and V delta is negative 10. Okay. Now, so when you do this math, you should come up with 50 watts here for negative 5 and 10. Okay, so this should be 1764 watts. 5 times 16 squared, that should be 1280 watts. And then this one, 20, so this would be 16 times 20. I better double check this one. Okay, so I got 16 plus 1.7 times negative 10. That's negative 1. We need to square that, so it becomes positive 1, so this gives me 20 watts. So now we just add everything together to 50 plus 50 plus 1764 plus 1280 plus 20. And so all of that, so all of these together is 3,364 watts power dissipated, which matches the power delivered that we calculated earlier as a check figure. So that's the answer to this problem. So make sure to like the Facebook page. Only 1 in 100 people who come to this channel and get help actually like something or give back. So make sure that you're not one of those people. Make sure you like this problem, the problem link, the link to the problem on Facebook if you got help on it, and to share the video, and at the very minimum, like the Facebook page so your friends can find us. The more people that find us, the more interactive a channel and a forum that we have. Okay? I'll talk to you guys later.